Okay, students, Assalamu alaikum. Let's start with our lecture today. Okay, so today's lecture is about another topic in fluid mechanics, which is dimensional analysis and similitude. So this is a specific topic that we are going to cover today. Normally, what happens is that if you want to design a fluid substance, or if you want to design a device which is involving fluid flows, we need to prepare a model of the device first, okay, and do the testing over the model. Now, in order to do the testing over the model for the fluid devices, a dimensional analysis is performed, okay, and the model is then tested based on the dimensional analysis and similitude concepts and theories. The most common example is that suppose if you want to test a new aeroplane, okay, so one way is that you design the aeroplane and then you make it fly and test it real time. But this is very costly. First of all, making a real-time aeroplane is costly. Secondly, you are doing it for the research purpose. You're doing it so there are chances that failures might occur. And if suppose the airplane is there in the air and you're flying the airplane and a failure occur, so it might result in casualties. Okay, so it's not really feasible to test the airplane by designing it and then flying it. Rather, what we do is that we develop a small scale model, and then small scale model is then tested in a controlled laboratory environment. Okay, but the controlled laboratory environment should be such that it could replicate, it could duplicate the conditions of actual environment. So in order to do that, duplication, we need to produce not just the model of the aeroplane, small scale, but also we need to produce a model of the conditions surrounding the aeroplane, the fluid conditions. Okay, so the airflow across the aeroplane should be for the case of the model should be such that it should be similar for the case of the real prototype. Okay, so in order to do that, we need to do the similitude analysis. Okay, and then what parameters need to be tested for experiments? This has to be determined based upon the dimensional analysis. So we determine some dimensionless parameters which actually reduce our testing significantly. Okay, so the testing experimentation cost is reduced by the dimensional analysis and similitude significantly. And sometimes it's not just about the economics, also it's about the safety. Okay, so you cannot really test something which has a chances of casualties at the failure, okay, in real time. So dimensional analysis and similitude is basically a topic of fluid mechanics. It's an important topic that we will cover, inshallah, today. This is basically chapter number 8 of your fluid mechanics textbook that we are going to cover today. So the outline is first we are going to discuss about the need for dimensional analysis. Then we are going to discuss about the dimensions and the equations. Then we are going to cover the Buckingham p-Theorem. If I'm not wrong, you have already covered Buckingham p-Theorem in one of your courses earlier. Then we are going to discuss a little about dimensional analysis. Then we're going to talk about common pi groups. And then finally, we're going to discuss the concept of similitude. The need for dimensional analysis. Fluid mechanics is heavily involved with experimental work because the analytical tools presently available are not capable of yielding exact solutions to many fluid flow problems. You cannot analytically analyze all the fluid flow problems. There are no such comprehensive equations that can actually solve all the real-time problems. Okay, so the best thing is that when you want to design something, to do the experiments. Okay, so experimentations are hugely involved in the course of fluid mechanics. Now, experiments are usually carried out on models of the structures. We develop models, okay, that guide the flow. Normally, the model is a small scale device. Okay, the real thing might be big. For example, an aeroplane might be an extremely big device, but when we need to do the experiments, we need to make a model small scale and do the experiments over that model. Okay. Similarly, for example, if you want to develop a car is a big thing. Rather than doing experiments directly over the car, what we do is that we make a small scale model of it first, and then do the experiments over the model and replicate the effects of the experimentation, and understand and analyze the effects of the experiments over the real model or the prototype. So a model is basically a subscale replica of the structure. Replica means duplicate. So a subscales means small scale. So a small scale duplicate of the structure is basically model. And when we talk about, once we do the testing over the model and we feel that we are now confident enough that we can produce that product, that design, we can actually generate that design in the real time. So what we do is that we produce or we generate or make a prototype. Now, prototype is a full scale device, but we make it just one to test and to analyze if our testing was done correctly. Okay, once a prototype is successful, then we do go for the mass production. So we don't normally go for the mass production until and unless we first judge the performance of our device or the performance of our product in the form of a prototype. Okay, a full scale structure employed in the actual engineering design is called the prototype. So the thing is that whenever you have a new design and you want to produce it on a mass scale, we don't produce it on a mass scale until and unless we generate a prototype and check if our design is working fine or not. And we do not produce our prototype until and unless we first test it on a small scale model to replicate that what should be the design parameters or conditions. Okay. So this is how things are related. We have the model, we have the prototype, okay, and so dimensional analysis is needed to produce the model. You cannot produce the model until and unless you perform the dimensional analysis over the fluid flow devices, okay, and fluid flow conditions. So the model subscale is usually made much smaller than the prototype for economic reasons, okay. So what is a model and what is a prototype? This is important for short questions point of view. Okay. Experimental studies are usually quite expensive, resource, time, and otherwise. In order to keep the required experimentation to a minimum, a technique called dimensional analysis is often performed. So when we want to reduce the number of experiments that are needed to be performed, okay, what we do is that we do a technique called dimensional analysis. Now, the dimensional analysis involves combining dimensional variables that define a problem into dimensionless groups. Okay, so what we do is that we combine some of the dimensional variables and make a dimensionless group. Okay, the dimensionless group provide correlation between model and prototype in terms of performance. They enable us to have an idea about the performance of the prototype based on the performance of the model. Okay. Okay, so to appreciate the advantages of using dimensionless parameters, let us consider the flow of water through the orifice as shown in the figure. So suppose let's try to understand that why do we need dimensional analysis? In order to understand that, let's take an example. Suppose this is the example of a flow through an orifice. So here we have the flow coming and it has to pass through an orifice. This is the orifice. Okay, so orifice is basically what? It's a small opening in a plate, in a pipe. Okay, so the flow has to flow through that opening, and that is basically an orifice. It is known that pressure drop across the orifice is a function of velocity, density, and diameters. So when you have the flow across the orifice, so there will be pressure drop. Okay, pressure drop across the orifice. Okay, and this pressure drop is basically a function of the velocity, depending upon what was the velocity of the flow, and the density. Okay, what material, what fluid was used for the flow. Okay, and the diameters. Okay, so diameters means what was the inlet diameter, what was the main diameter of the pipe, and then what is the diameter of the orifice. Okay, so these are the parameters based on which the pressure drop will depend. So if one of the parameters is going to change, the pressure drop is going to change. To find the dependence of delta P on these parameters, we probably have to run experiments at different values of each variable. This will lead to a huge number of experiments, binomial coefficient, with huge associated cost. So suppose if I want to know that what is the dependence of these variables, what is the dependence of delta P, pressure drop, on these variables, what we need to do, we have to fix all the variables and first starting changing one. And we change it multiple times and do the experiments. Then we change one of the other variable and then start repeat the experiments again and again. Okay, so we have to fix variables and change all the variables and do all the experiments in order to actually judge that what is the dependence of pressure drop over these variables. Okay, so basically the binomial coefficient can actually predict how many experiments are needed to actually judge the dependence of delta P on those variables. So for example, let's say that each of the variable, velocity, density, diameters, has to be tested for 3 values, minimum required to define a curve. If you want to define a curve, you need at least 3 values. Okay, because two points are there, that's going to make the line. But if there is a curve, a third point must be there to ascertain if what is the kind of a curve. Okay, so that's the minimum requirement to have a curve. You need to have at least 3 points. Okay, so we are just talking about the minimum values of experiments that are needed. So thus the total number of values will be, because we have 4 variables and we need 3 experiments for each. So 4 multiplied by 3, that means 12 number values are needed. Okay, for each variable. Then the total number of experiments that which needs to be determined, which can be determined by the binomial coefficient, which is NR. Okay, so n factorial by r factorial into n minus r factorial. So if we just put the values, you're going to come out to be like 495 experiments are needed to actually find out what is the dependence of pressure drop on these variables, velocity, density, and the 2 diameters. Okay, so a lot of experiments are needed. Obviously, experiments are conducted on real-time lab scale apparatus, and obviously it's going to take time and it's going to take the efforts as well as the economics, and the cost will be involved. So these costs are significantly these costs are significantly reduced if we reduce the number of experiments needed. So what we do is that we develop a we perform dimension analysis and we develop dimensional groups. Now, instead of saying that, okay, we want to find out what is the dependence of delta P over those 4 variables, what we do is that we try to determine what will be the dependence of this dimensionless parameter over these 2 dimensionless parameters. Okay, so this is going to provide the exact dependence of delta P over the other variables the same way as it would have done in the previous case. But since now we have developed the dimensionless variables, so because of having dimensionless variables, so the number of parameters have reduced. Okay, so now it's just 1 parameter depending over 2 parameters. Okay, previously we had delta P, which was dependent over 4 parameters: velocity, density, and 2 diameters. Okay, so if you apply the binomial coefficient, binomial expansion, okay, So you're going to find out that the number of experiments would be significantly reduced. Okay, so this will lead to a substantial reduction in the number of experiments needed since each dimensionless parameter is treated as a single variable. So in order to get the dimensionless parameters, what we do is that we do the dimensional analysis. Okay, so that's basically the significance of dimensional analysis. Okay, so what is the significance of dimensional analysis? The significance of dimensional analysis is that it can reduce the number of experiments needed. Okay, so thus reducing the overall cost of experimentation and the time required to do those experiments. Okay, so this is the answer for this. Obviously, this could be asked in a short question. Okay, dimensions and equations. All variables used in science or engineering are expressed in terms of a limited number of basic dimensions. For most problems, the basic dimensions are the mass, length, and time. These are the things that you have studied in chapter number 1. And while we were studying that in chapter number 1, I told you that we are going to return back to this topic when we will be studying the dimensional analysis. Okay, so the dimensions of all other variables can be expressed in terms of the basic dimensions. The basic dimensions of some common quantities of interest in fluid mechanics are listed below. For example, velocity, it is length by time, acceleration, length by time squared. Then you'll have force, angular velocity, flow rate, pressure, density, specific weight, viscosity, work, surface tension. Now, the question is that if a problem comes in the exam, will these dimensions be provided for these quantities? Okay, what will be provided to you will be a list of formulas and some dimensions which are provided at the back of your book, the way it was provided in the midterm exam. So if a quantity is there within that list, then that quantity will be provided to you in the exam. But if that quantity is not there in the list, then that quantity will not be provided to you in the exam. So at the back of the book, you have some formulas as well as some dimensions and their some quantities and their dimensions provided. Okay, I will exactly provide that page, those 3-4 pages to you. Okay. So if a quantity is there in those pages, then that dimension is there provided to you in the exam. If it is not there, then it will not be provided. Okay, so as simple as that. Also, I'm going to upload that formula sheet, which will be provided in the exam on GCR today. Okay, so GCR you can also check where I provide the textbook. I will also provide the formula sheet. Okay. So you can just have a look at which formulas be provided to you in the exam. So no need to ask, is it provided or not provided? Check the formula sheet. If it is there, provide it. If it is not there, not provided. Okay. When a variable is enclosed in square brackets, its dimensions is being referred to means the dimensions of viscosity so whenever we write anything in closed brackets, then we consider that we are actually considering its dimensions. So dimensional homogeneity means that each term in an equation has the same primary dimensions, and this is true for the case of units as well. If you have an equation and so each term should have the same set of units. Okay, so that's the dimensional homogeneity. Or units homogeneity that should be there. So for example, apply dimensional homogeneity to the density form of the ideal gas law, which is P equals to rho RT. So P is M over LT square, rho is M over L cube, R is L square over the theta T square, T is theta. So you can just apply all the dimensions to the variables, and well, you can see the right hand side is actually equals to the left hand side. So P is M over LT square, and rho RT, if you substitute the values, is also going to come out to be M over LT square. So that's the dimensional homogeneity. So the equations on the right hand side and on the left hand side should have the same set of dimensions, and each term in it should have the same set of dimensions. Now, Buckingham p-Theorem, a dimensionless group. So here we define a dimensionless group as pi. Okay, and what we need to do is we need to actually what we need to do is we need to find out what is this dimensionless group for our set of problems, for our set of variables in the problem. Okay, so let us define a dimensionless group. We call it pi. And since this methodology was developed by Mr. Buckingham, so that's why it is known as the Buckingham pi theorem. Okay, so the Buckingham pi theorem says that suppose if you have a situation where one of the variable is dependent upon other variables, okay, and let's say you have one variable and it is dependent upon from 2 to n variables, then how many pi groups are needed? Pi groups are needed depends upon how many number of basic dimensions are there in it. Okay, so well, whatever the number of basic dimensions are, let's say the basic dimensions are n and total variables for n, so number of pi groups will be n minus n. Okay. Since here things are written in the form of variables, it will be a little hard to understand right now, but once we're going to start solving the problem, things will become much more clear to you. Okay. So there are two methodologies mentioned which could be used to solve, which could be used to find out the dimensionless parameters. Okay. One methodology is the step-by-step method. The other methodology is the exponent method. Now, suppose if you have a problem in the exam and it is mentioned that use step-by-step method, then you have to use a step-by-step method. Suppose if it is mentioned in the problem that use exponent method to find out the dimensionless parameter, then you have to use the exponent method. But suppose it is not said anything, it's not said that use a step-by-step method, neither it is said that use the exponent method, then you are free to choose whichever method you want to choose, you can choose. Okay, so we are going to learn both the methodologies, step-by-step method as well as the exponent method. Okay, so let's first start with the step-by-step method. So there are basically some of the steps that needs to be performed, and I'm not going to go through those steps, they are listed down here, but it's better to directly solve the problem, and it's going to explain things much better, that how the step-by-step method is performed. Okay, so the problem is that we have a situation that the side thrust of a rough spinning ball in a fluid. We need to find out the pi group for this. Okay, so we have a ball. The ball is spinning with an angular velocity omega. The diameter of the ball is d. Okay, and obviously it is moving, so there is going to be a relative velocity of air which will be going across it. Okay, and since the relative velocity of the mean stream velocity is v naught, so there's going to be a drag. Okay, so there's going to be a drag over the ball, and that drag force is represented by F. Okay, now we need to find out the pi group for this solution. Okay, here we know that this force is basically a function of diameter, velocity, density of the fluid, viscosity of the fluid. Okay, then surface roughness of the ball, how rough is the ball, how smooth is the ball, and the angular velocity of the ball. We know that these are the parameters for which the force, drag force, depends on, and we need to find out that what are the dimensionless parameters that we can produce out of it. Now we need to find dimensionless parameters such that one of the dimensionless parameters should be this F over rho V naught squared D squared, and we need to find it as a function of other dimensionless parameters. Okay, so we need to find what should be the other dimensionless parameters that could be used in the modeling of this rough spinning ball. So the problem solution starts like this. First of all, we need to know that how many are the variables involved in it. Okay, so since if you look here, so we have 1, 2, 3, 4, 5, 6, 7. So I will call here the total number of variables involved are 7. Okay, so that's the first step. How many variables involved here? So force is a function of diameter, velocity, density, viscosity, roughness. and angular velocity. Okay, so angular velocity is of the ball, velocity is of the air across it. Okay, so if I just count them, so 1, 2, 3, 4, 5, 6, 7. So total number of variables are 7. So that's the first step. How many number of variables are there? 7. Okay. Now the next step is that what we need to do is we need to write the basic dimensions of all those variables involved. So like for example, for force, it is ml by t squared. Now you can determine it. How is it? It's ml by t squared. Okay, this is something that we covered in chapter number 1 as well. Okay, and also you will have a list of quantities with you in the exam for which the dimensions will be provided. But anyways, you have to look at it with which one will be provided, which is not provided. And if it is not provided, then you have to bring it from your mind. Okay, so we went through it, we worked through it in chapter number 1, that how you determine the basic dimensions for any parameter. So for the case of force, it is ml by t squared. Okay, for the case of diameter, it is only length. For the case of velocity, it is L by T. For the case of density, it is M by L cubed. Then for the case of viscosity, it is M by LT. For the case of roughness, it is just length. If you remember, relative roughness was Ks by T when we were studying the Moody chart. So D was the diameter and Ks was the roughness. And I told you that what roughness is. So whenever you have an uneven surface, so you just check that what is the amplitude, what is the height of unevenness. So it's basically length. So dimensions of length. Then we have angular velocity. So angular velocity will have units 1 over t. Okay, angular velocity is just per second. So these are the dimensions here. Now let's see that how many basic dimensions do we have. We already established that n is equals to 7. Now m are the number of basic dimensions. So now if you look here, we have m. If I write down here that how many basic dimensions we have here, we have m, we have l, we have t, then l, t, m, l, t, l, t. So it's just m, l, t, 3 basic dimensions. So our m will be 3. Okay. So once I know what are the basic variables, and then we know that what are the basic dimensions, then we can find that how many pi variables, how many pi dimensionless parameters can be made. And the number of pi dimensionless variables or parameters will be n minus m, which will be 7 minus 3, that will be equals to 4. So 4 will be the pi variables that will be made by using the Buckingham pi theorem. So that's the first step. Okay. Now, if you look here, for out of those 4, 1 is already specified in the question. So 1 is mentioned that one variable should be this one. This is, let's call it pi. If I'm saying that this is pi 1, this is pi 2, this is pi 3, then let's call this as pi 4. Okay. So we need to have pi 1, pi 2, pi 3, pi 4. Pi 4 is already defined in the problem statement. Okay. And we need to find out pi 1, pi 2, and pi 3 if pi 4 is this one. Okay. So this is the first step. Okay. The first step was to write all the variables. Okay. Now what we need to do is, this is a step-by-step method. So in each step, we are going to eliminate one variable. In each step, we are going to eliminate one variable. Okay. Now, if you look here, the most simplest one here is either the diameter or Ks, because they are just L. So we can use either diameter or Ks to eliminate length from the whole, from all set of variables. Okay. So what we can do is that we will use the first. We want to eliminate as a first step, we will eliminate length. And what we are using to eliminate length, we will use length as D to eliminate. Okay, we're going to use length as D to eliminate. So one by one, let's talk about this. If I divide diameter by diameter, then it's just 1. So length eliminated. Okay, so D by D will have length eliminated, or instead of writing here like this. Okay. So D by D is just 1. Length eliminated. Okay. Let's talk here. ML by T square. Now, if I want to eliminate L, I need to divide by L. So what I'm going to do, I'm going to divide F by D. So if I say F by D, so it will become what? It will become M over T square, length eliminated. Okay. Now let's see here. It is L by T for velocity. If I want to eliminate L, I have to divide by D. Okay, so it will become V by D. So it will become 1 over T dimension, right? Eliminated length. Now here in this case, density is M by L cube. If I want to eliminate length, I have to multiply by L cube. Okay, so what I'm going to do, I'm going to multiply rho by D cube. So it becomes M. Is it clear? So length cube is eliminated. So look, here V was L by T. I want to eliminate L. So I have to divide by L. But L I am representing as D. D by D. So it was D. D was as L. So I had to remove L. So I had to divide by L. But I am representing L as D. So D by D, length eliminated. It's just 1. Okay. So here, density was M by L cube. I have to multiply by L cube. But L I am representing as D. So multiply by D cube. So length eliminated. Now it's just M. Okay, let's talk about here viscosity. M by LT. I want to eliminate L. So I had to multiply by L. But L I am representing as D. So multiply by D. It should be mu D. And that will be M by T. Okay. Then Ks by D. That will be 1. Here there is no L. So I'm going to keep it as it is. No change. Omega S as 1 by T. First step done. In this step, eliminated L. Is it clear? First step done, eliminated L. Now let's move over to the second step. Now we need to eliminate another basic variable, another basic dimension. Okay, now look here. We have M by T square, 1 by T, M by T, 1 by T. M is the most simplest one. Let's eliminate M. Okay, so now the next thing is I want to eliminate M, but whenever I have to eliminate M, I'm going to represent M as rho D cube. Is it clear? So the next step, I have to eliminate M. So here it was F by D was M by T square. If I want to eliminate M, I have to divide by M. That means divide by rho D cube. Okay, so F by D divided by rho divided by rho D cube. So what I'm going to be left up with? F by D divided by rho D cube. Okay. So it would be F by rho D power 4. F by rho D power 4. Okay, and the units will be 1 by T squared. Is it clear? Okay, now here it was already eliminated, nothing is there. So just keep it as it is. Okay, skip it. Now here, 1 by T. There was no M here. So keep it as it is. No need to do anything. V by D is equals to 1 by T. Okay. Then rho D cube by M equals to M. Okay, divide by M. So divide by rho D cube. So it becomes 1, right? So that will turn out to be 1. Here, mu D was N by T. Divide by M means divide by rho D cube. So it will be mu D divided by rho D cube. Basically what? Mu by rho D square. And the unit will be 1 by T. Right? Ks by D was already 1. And here there is no M. So we're going to keep it as it is. Omega S is equals to 1 by T. So in the second step, we have eliminated M. So first we eliminated L, then we eliminated M. So now we just have T. Now we just have T. So what we can do is that we can now eliminate T. Okay. So now which variable should we use to eliminate T? It's up to us. It's up to us. We can use any of the variable. But the thing is that we have to look for the fact that we have to come up with this dimensionless variable. F by rho V square D squared. Okay. So one of the variable was provided. Okay. So how can I get this variable? So I have here this thing, F by rho D power 4. Okay. So now what I need is I need to so F by rho V square D square. Rho. Yes, we are going to do this. We are going to take V by D. So basically we need to eliminate 1 by T. Okay. So let's eliminate 1 by T and use for 1 by T we use V by D. Okay. So here I have 1 by T square. Okay. Or instead of writing it like this, to make it simple for you, let's eliminate T. Okay, and so for that, T should be D by V, right? So here I have 1 over T square. Here I have 1 over T square, okay? So I have to multiply by T square to get it, okay? Multiply by T square means multiply by D square upon V square. Okay, so let's do it. F by rho D power 4 multiply by D square upon V square. So what we're going to get up is F D square was going to be by this F upon rho D square V square. And now it's dimensionless. There is no dimension here. And if you look here, we have actually achieved one of the dimensionless parameter which we wanted to achieve. Okay. So we've got this as one dimensionless parameter. Okay, V by D, if you multiply by T, which is D by V, so it will become 1. Okay. This was already 1. Here it was mu over rho d square was 1 by t. We have to multiply by t. Okay, so that means mu over rho d square multiplied by t was d by v. Okay, so this d will be cancelled by this. So it will become what? Mu over rho d v. Okay, this is our another dimensionless parameter. Okay. Then here it is just 1, and here it is 1 by t. Okay, so we have to multiply by t. Okay, so we have to multiply by t. So it's omega s into d by v. Okay. So what are the dimensionless parameters that we actually get? So this is one of the dimensionless parameter that we get. This is another dimensionless parameter that we get. Okay. Okay, ks by d is another dimensionless parameter that we get. Okay. And the third dimensionless parameter is this, omega s d by v. These are the dimensionless parameters that we get. So let's have a look at it. So you see here we get, this is one dimensionless parameter, this is the second dimensionless parameter, ks by d was another third, and omega d by v was the fourth. So we have, this is our pi 1, this is our pi 2, this is our pi 3, and this is our pi 4. And we wanted to find what was pi 4 as a function of pi 1, pi 2, and pi 3. So we did the problem, we determined the dimensionless parameters using a step-by-step method. Okay. So that was required. Find pi 1, pi 2, and pi 3 as a function of pi 4. So that was the step-by-step method that we performed. And these are the pi variables that we determined. These are all dimensionless parameters. Okay. So there are no dimensions for it. So our answer will be this. This will be our answer. So f over rho v square d square is a function of rho v d upon mu ks by d omega d by b. Okay. So the problem is solved here at this point. Is there anything within this problem's solution which is not clear to anybody? Please feel free to ask. How is it rho v d mu? Okay, this is a good question. How is it rho v d by mu? Look, when we say it is a dimensionless parameter, means the same dimension at the numerator and same dimension at the denominator. They're canceling each other. Okay, so force by force, or length by length, or time by time. So dimension-wise, it does not matter that if you write numerator at the top or denominator at the top. So it could be written as mu upon rho vd, or could be written as rho vd upon mu. There is a reason why they have written it as rho vd upon mu, because rho vd upon mu is basically the formula of Reynolds number. Okay. So our answer was getting mu upon rho vd, but mu upon rho vd could also be written as rho vd upon mu, because dimensionally they are equal. Dimensionally it does not matter. The numerator is the same as the denominator. So we are not writing the values. Okay. So 2 is not the same as 1 over 2. 2 is not the same as 1 over 2. But because 2 is a value, right now we are not placing values. We are just saying dimensionally, the numerator and denominator are same, so it's dimensionless. So numerator could be written in place of the denominator, denominator can be written in place of the numerator, and it would still remain dimensionless. Is it clear? Okay, so that was one of the problem. Okay, now let's look at the other problem. This is a much rather simpler one. Okay, there are 3 significant dimensionless variables for a body falling in a vacuum, no viscous effects: the velocity, the acceleration due to gravity, g, and the distance through which the body falls, h. So we have v, g, and h, 3 variables specified in the problem. Find the pi group using step-by-step method. So for the case of velocity, it is L by T. For the case of acceleration due to gravity, it's basically 9.81 meter per second square, so that's L over T square. And we have height, which is L. Okay. So if we do it in a step-by-step manner, okay. So first thing is that we need to find how many number of variables. So n is basically 3. Okay. So now we can write the dimensions of each: L by T square, L. So how many basic variables? We have L, we have T. That's it. Okay. So M is equals to 2. Okay. So that means n minus m is equals to 3 minus 2, which is equals to 1. So how many pi groups will be there? There will be only 1 pi group. That will be right. Okay. So now next thing is that we have to eliminate one variable at a time. So if you look here in the first step, the most simplest one is L. So let's eliminate L, and we represent L as H. So here it is L by T. We have to divide by L, means divide by H. So it becomes V by H. Here it is L by T square. We have to eliminate L, so we have to divide by L. So that means divide by H. So it becomes G by H. And H by H is 1. It's already eliminated. So now we have eliminated L. Now we have 1 over T as V by H. Another 1 over T square is G by H. As I told you, it's up to you the way you want to use it. Okay, you can use any of the variables now because we want to eliminate T. What they have done is that in this problem, they have used this variable to eliminate T. So saying that 1 over T square is G by H. So T will be H by G under root. Okay. So now if you want to eliminate T, so you have to multiply by T. Multiply by T means multiply by V by H multiplied by T is H by G under root, which will be equals to V. Now H, and here above is H under root. So they're going to cancel each other because H is equals to H under root into H under root. So one of the H under root is going to be cancelled. It becomes V upon G H under root, and we get this thing here. Okay. So it's up to you which one you want to use. Okay. So this is a step-by-step method for this simpler problem. Okay. This is the same problem that we just did before. The drag force of a sphere in a fluid flowing past the sphere is a function of viscosity, mass density, velocity of the flow, diameter of the sphere. Use the step-by-step method. So that's the same, which we did before. Okay. So we have got this as a function of this, and that's it. So here, actually, it is a comparatively much simpler one. Okay, because here it is mentioned that FD is a function of mu, V, density, and D, just 4 variables. Previously, where the problem that we solved, we said that it was mentioned that F was a function of D, V, density, mu, Ks, and omega. So it was n was 7. Here in this case, n is basically 5. If you have n just 5, because you have FD as 1, viscosity 2, density 3, velocity 4, diameter 5. So n is 5. Basic dimensions would again be 3. So 5 minus 3 is 2 pi variables will be there. So one of the pi variable will be this one. Other pi variable will be this one. Okay, but it's the same problem, but comparatively simpler one. Okay, which is here. So the first method is done here. Now we are going to move towards the second method, which is the exponent method. Okay, the step-by-step method is done. If there is anything within the step-by-step method for dimensional analysis which is not clear to anybody, please feel free to ask. Is it clear? Okay, let's start the next topic, which is the exponent method in the dimensional analysis. So basically in the exponent method, it involves solving a set of algebraic simultaneous equations that derive from the requirement of dimensional homogeneity for equations describing physical systems. It's better, let's directly look at it from the perspective of a problem. The exponent methods, what are the steps that are needed are mentioned here, but it's better to just directly go through the problem and start solving. Okay, so let's say that we have a situation here that the force on a satellite in the Earth's atmosphere, this is something that we need to find out. So we need to find out force on a satellite in the Earth's atmosphere. We need to find out the non-dimensional form of the equation where F is a function of the lambda, rho, D, and C. Okay, so C is basically what? It is the speed of light. D has the dimensions of length, rho is the density, and lambda is also a wavelength. So it's basically also length. Okay, so what we need to do is that what we need to write an equation of the format like this, where F is equals to lambda rho dc, where the powers are of lambda rho dc will be A, B, C, and D. Okay. So F is equals to lambda A power A, rho power B, D power C, and C power D. Okay. Now then what we need to do is we need to write down the basic dimensions of each variable involved. So F is ml by T. F is ml by T. Lambda will be L. Rho will be m by L cube. D will be again L, and C will be L by T. So it will be ml by T square will be equals to L power A, m over L cube power B, L power C, L by T power D. Okay. Now we have to write it in, it's better to write it in a specific one-line equation format. So I will write here like LMT minus 2 instead of writing ml by T. I'm going to write here LMT minus 2. Then I have to add up all the exponents for L. Okay, so L will be A, here it will be minus 3B, here will be C, here will be D. So L will be A minus 3B plus C plus D. Okay, N will be on this side of the equation, it will be B only, and T will be on this side of the equation, it will be minus D. So L and T minus 2 will be equal to L A minus 3B plus C plus D, M power B, and T minus power minus D. Now what we need to do is we need to equate the exponents, because this is the exponent method. Now we need to equate the exponents, and all the exponents should be equal to 0. So when all the exponents are equal to 0, then it becomes a dimensionless parameter. Okay. So for this case, we are going to make the equations. So we are going to have 3 equations here. One equation for L. So L equation for the equation for L says that A minus 3B plus C plus D is equals to 1. The second equation for M will be B equals to 1. And third equation for T will be D minus D equals to minus 2. Okay, so from this we know that the value for D will be 2, B will be 1, and if I substitute the value of D and B, so I can get A as a function of C. So A will be equals to 2 minus C. So if I just substitute the values, so F is equals to lambda 2 minus C, rho power B, B is 1, so it's just rho, D power C, and C is just C, okay, and then C's power D, where D is 2, so it becomes C squared, okay. So we get now we get the variables as F over rho C square over lambda squared. Wherever the negatives were, we kept it as less separated. So power C, we kept it on one side of the equation. So it becomes F is equals to lambda square into lambda power minus C rho D power C squared. Okay, so this is with exponent minus C, and this is with exponent C. We can combine them together. It becomes D upon lambda power C, and rest are without exponents C. So they are going to be taken on the other side of the equation. It becomes F over lambda square rho C squared. So you get this as one dimensionless parameter, this one as the other dimensionless parameter. So we get 2 dimensionless parameters, one as a function of the other. Okay. So this is basically the exponent method. In the exponent method, what we need to do is that we need to write one variable as a function of other variables. Put the exponents A, B, C, D, whatever be the number of variables, put the exponent to all those variables. Okay. Then write down the basic dimensions of each of the variable, and then equate the exponents on each side of the variable. Okay, left hand side equals to the right hand side. Okay, so you're going to get the number of equations equals to the number of basic dimensions. Okay, and then corresponding to that, you can actually solve for different variables. So this is one question for the exponent method. You can have the same equation that we solved it using the step-by-step method. We can also solve it using the exponent methods. Let's have a look at the solution here. The drag of a sphere in a flowing fluid is a function of velocity, fluid density, fluid viscosity, and the sphere diameter. So FD is basically a function of V, rho, mu, and D. Okay, so find the pi groups using the exponent method. So when you have to use the exponent method, the first thing is that we need to see that what are the basic dimensions of each of the variables. So we have F, V, velocity, density, viscosity, and length. So the basic variables are M, L, and T. So since we have 5 total variables, so N is equals to 5, M is equals to 3, because base variables are just M, L, and T, so that will be 3. So N minus M will be 2. So we'll have 2 pi groups here. Okay. So now we have to just write the equation in the format F is equals to. So we have to write the equation in the format F D is equals to V power A, rho power B, mu power C, and D power D. Okay, Then we have to write down the basic units for these. So basic unit for f is ml by t square, then l by t power a, then m by l cube power b, m by lt power c, and l power d. Then we have to write it in the linear format. It's better to write it in the linear format. So linear format will be what? You have m, l, and t. So it will be m, l, t power minus 2 will be equals to where we have m. So m we have here, it will be b plus c, that will be m, b plus c. Okay, so here we have m with b, m with c. Okay, then multiply by L. So for the L, you'll have a minus 3b, a minus 3b minus c plus d. So it will be a minus 3b minus c plus d multiply by t. So for the case of t, it will be minus a minus c. That's it. So it will be t power minus a minus c. Okay. So now just we need to equate the exponents for each of the variables, for each of the basic dimension. So if we equate for m, so 1 is equals to b plus c. Okay. When we equate for L, so 1 equals to a minus 3b minus c plus d. When we equate for t, it will be minus 2 is equals to minus a minus c. Okay. So we got here 3 equations here. Okay, and we have 4 variables. So we can put all the other variables as a function of one of the variable. Okay. So here what we can do is we have these 3 equations here. Okay, we can find it as a variable of d. Let's say d, we can take it as a variable. We can find a as a function of d, b as a function of d, c as a function of d. Okay. So this is just a small problem of mathematics. If you do it like this, then a will be equal to d, b will be equal to d minus 1, c will be equal to 2 minus d. Okay, then we can write again here. Previously we have written f is equals to v power a, rho power b, mu power c, d power d. So now just we have to write down the values of these variables. So b power d, because a is equals to d. Rho power b. So here it will be b is d minus 1. So rho power d minus 1. Mu power 2 minus d. And d power d. Okay. So we got this here equation. Now what we can do is that wherever we have exponent d, we keep it on one side of the equation, others we keep on the other side of the equation. So f, okay, d is here, then rho power d power minus 1. So here we have, you can say it like this, right here. Okay, so f is equals to v power d, rho power d, rho power minus 1 into mu power 2, mu power minus d into d power d. So all the powers with the d on the one side and others on the other side. Okay, so it will become f multiply by rho, because it is 1 over rho here at this end, so it will go on the other side. Then divide by mu squared. So f multiplied by rho divided by mu square. This becomes 1 parameter, and then all power d as the other parameter. So you got this 1 parameter, this as the other parameter. So this is how we solve it using the exponent method. As I've already mentioned you before, that suppose if it is said in the problem that use a step-by-step approach, then you have to use a step-by-step approach. If it is said in the problem that use the exponent approach, then you have to use the exponent method approach. But if it is nothing said in the problem, whether you use a step-by-step or exponent method, then it's your choice, whatever the method you want to choose. Okay. So this is one problem using the exponent approach. We did. So that's it. So we have done the exponent approach. We are already done with the step-by-step approach as well. Now let's discuss a little about the common pi groups. There are different pi groups available. Pi groups are the dimensionless groups, okay, and dimensionless groups are basically used to model different fluid flow processes, fluid flows phenomena. Okay, so the common pi groups are the pressure coefficient. This is one of the common pi group. Okay, again, whenever you have a pi group, this is a dimensionless group. Itself, the group does not have any dimension. Okay, so it's dimensionless. So friction or shear stress coefficient is represented by this group. Then we have Reynolds number, the one which you have already gone through in different chapters and solved problems related to it. So Reynolds number, this is also a pi group. Then we have Mach number. Mach number is normally used when you have very high velocities. Okay, so Mach number, this is another pi group. Then we have Weber number. Weber number is another pi group. Okay, and Fraud number. Fraud number is another pi group. Okay, these are some of the numbers, some of the ones which you have already used, some which you have not used. Okay, but this is just basic information of whatever the pi groups that we have. Okay, now we have different set of forces. Okay, basically what's done is that each dimensionless quantity, each pi group is a ratio of two forces. They are dimensionless groups because the numerator is also a force and denominator is also a force. And so the force cancels each other and it becomes a dimensionless group. So what we say is that all of these dimensionless parameters are basically the ratio of forces. Now, what kind of forces that we are dealing with here? We have the inertia force, which is F as a function of ma. So this will be the dimension parameter for the inertia force. Then we'll have the pressure force. We have the viscous force corresponding to the equation of the viscosity. We have the surface tension force. We have the gravity force. We have the elasticity or compressibility force. Okay. So basically, whenever we are talking about those dimensionless parameters, so they are basically a ratio of two forces. For example, Cp, which was the pressure coefficient, is basically a ratio of pressure force by inertia force. We have the friction or shear coefficient. It's basically a ratio of shear stress to dynamic pressure. We have Reynolds number, is the ratio of inertia force to viscous force. We have Mach number, it's the ratio of inertia force to compressibility force. We have Weber number, it's the ratio of inertia force to surface tension force. We have Fraud number, it's basically a ratio of inertia force to the gravity force. Okay. So as mentioned, that all of these ratios or dimensionless parameters are basically the ratio of two forces. Okay. Now the point for you to memorize for short questions is, since you have been using Reynolds number, so where is the Reynolds number used? Reynolds number is used whenever viscous forces are involved. So if you have a flow where viscous forces are involved, viscosity is there, Reynolds number is a must. Okay, so for viscous forces, for flow with viscous forces, Reynolds number is used. Okay, for flow where the compressibility effects are there, because normally when the rockets or air is moving at a very fast speed, so they're moving through the air, so air becomes compressed comparatively. So compression forces are too much there at very high speed. Okay, so whenever you have the compressibility effects involved, Mach number is a must. That must be used. Okay, whenever you have a free surface flow, for example, river flowing, whenever a river is flowing, there is a free surface of the river which is in contact with the atmosphere. Okay, sometimes you have a duct which is partially filled with a fluid and the fluid is flowing. Again, there is a free surface. So whenever you have a free surface, the gravitational force is very important because this gravitational force actually influences the flow pattern. How the flow pattern is going to look like depends upon the gravitational forces. So in those cases, Fraud number is very important. It needs to be considered. Then, for example, if you have cases where surface tension is very important, like for example, in liquid atomization. Okay, so you're spraying the liquid and the liquid is atomized. Okay, so surface tension becomes quite more significant in those kind of fluid flow problems. So then the Weber number will be very important. So which number is important for what kind of case? This is something which is important for you to memorize for the short questions point of view. Okay. So Reynolds number is important if it is asked that suppose if it is a viscous flow, then which number is important? Reynolds number. If it is a free surface flow, where gravitational forces are important, which number is important? Prod number. If it is a flow where the surface tension effects are more significant, okay, like for example in liquid atomization, which number is important? The Weber number. So if you have a case flow where the compressibility forces are more significant, cannot be ignored, then which number is important? Mach number is important. So this slide itself is important for the short questions point of view. Okay, can ask you in the questions in a similar way as I have described here. Okay. So that was about the dimensional analysis, and we have covered the topic of dimensional analysis completely. Now let's discuss a little about similitude. We are not going to go into much details of the similitude itself, but similitude is basically coming from the word similar. Okay, so similitude is a theory and art of predicting prototype performance from model observation. Okay, so for example, you want to design an aeroplane. For designing an aeroplane, real size, it's too expensive. The airplane is a very big device, a very big equipment. Okay, so it's better to first make a small size model which you can test in your lab and predict the performance of your device, of your model in lab, and then after that replicate or analyze that if your model is behaving like this under these conditions, how would the real object is going to behave under the real conditions? To relate the real conditions with the model conditions, okay, and that is similitude. Okay, so for example, you modeled an aeroplane and tested in a wind tunnel inside your laboratory and find out that when the velocity was 2 meters per second, your model failed. It fell off. It couldn't sustain the drag forces. Okay, so if your model, it was such a small scale model, was not able to withstand 2 meters per second air coming off, then the real prototype, the real scale device, what should be the speed of the air that it won't be able to sustain? Okay, so this is basically similitude. Okay, so you are actually comparing your model conditions with the real-time conditions. Okay, and based upon the testing on your model, you are judging that what are the limitations of your real-time device. Okay, so this is similitude, and it's very important for fluid flow analysis. Similitude is a theory and art of predicting prototype performance. Prototype is the real thing, the real full-scale device that you have designed, that you make. Okay, so predicting the prototype performance, you have not made the prototype yet. Prototype is going to be very expensive. So you have made a small-scale model, and you want to predict that how your prototype is going to perform based on your model observation, because you are going to make the testing on your model. You're not going to make the test on the prototype. You're going to make the testing on the model. Okay, so theory of similitude involves the application of dimensionless numbers, so Reynolds number, Prod number, to predict prototype performance from model tests. There are different types of similarities that needs to be taken into consideration, but we are going to focus here over two: geometric similitude and dynamic similitude. Okay, dynamic similarity and geometric similarity. These are the ones which we are going to consider. So when we talk about the geometric similitude is basically what? The ratio between the model and the prototype should be same for all the geometric parameters, for all the lengths, for all the dimensions. It should be same. Okay, so if this is your prototype and you're making a small scale model of it, then each dimension of the small scale model, the ratio between each dimension of prototype to each dimension of the small scale model should be same, should be constant. Okay, so we call it length scale ratio. So we have to determine the length scale ratio, and based on the length scale ratio, your model is going to be developed, designed to replicate the conditions of the prototype. Okay, so this is the geometric similitude. So if you have, once you have the length scale ratio, correspondingly you can find out the area and volume ratios as well. So area ratio will be L, length scale ratio is square. and so that will be the conversion factor between the model and the prototype. And similarly, for the case of the volume, the conversion factor will be length scale ratio power 3. This is the geometric similitude. Okay. The next thing is the dynamic similitude. The dynamic similitude says that the forces that act on the corresponding masses in the model and prototype must be in the same ratio. So the forces which are acting on your model and the forces which are acting on the prototype, the ratio of those forces should be same. Okay, the ratio of those forces should be constant. Okay, so we have whatever the forces involved, the ratio of those forces should be constant. Since the forces acting on the fluid elements will control the motion of those elements, so it follows that the dynamic similarity will yield similarity of flow patterns in the prototype and model if the prototype and model are geometrically similar. So what do we mean by that? We mean by that the inertia force for the model and inertia force for the prototype, their ratio should be the same as the pressure force for the model by the pressure force for the prototype. Should be the same as the viscous force for the model by the viscous force for the prototype. Should be the same as the gravitational force for the model by the gravitational force for the prototype. So these force ratios between the model and the prototype should be the same. Now, since we know that certain dimensionless parameters are basically the ratio of two forces, okay, so now we can rearrange this equation. So if we rearrange the equation, so that means we can say that the inertia force by pressure force for the model should be the same as the inertia force by pressure force for the prototype. That means the pressure coefficient for the model and the pressure coefficient for the prototype should be the same. Similarly, Reynolds number for the model and Reynolds number for the prototype should be the same. That means the Froude number for the model and Froude number for the prototype should be the same. So all these numbers, dimensionless numbers, if they are same for the model and the prototype, that means that the dynamic similitude is there. We are actually modeling the forces over our model compared to the one which is there over the prototype. Okay, so this is dynamic similitude. Here we have the geometric similitude. There is one example of a dynamic and geometric similitude in this chapter, but let's skip that. Okay, just the basic knowledge of what does similitude means and how do we relate the dynamic similitude and geometric similitude between the model and the prototype. Basic knowledge is important. Okay, so let's skip the example here for the case of similitude, and with this our topic of dynamic dimensional analysis and similitude is finished. Okay, so here we have the homework problems for it. That's it regarding this chapter. Now, if there is anything that you want to ask regarding the things that we studied in this chapter, please feel free to ask. Okay, so we are going to end our lecture here, and next we are going to have the quiz that we are supposed to have. Okay.